In video 15b, we'll talk about tools to solve buckling problems. In the last video, we described how to calculate the Euler buckling force for a column on a hinge in a pin. This applies anytime you have a situation where the two ends of the column are being pushed or pulled towards each other. We learned in the last video that the critical Euler buckling force for a beam held on a hinge in a pin is Fc equals pi squared times the flexural rigidity divided by the length squared. We learned that buckling is a half sinusoid with arbitrary amplitude for any force above the critical buckling force, and that at larger forces the beams bend so much it exceeds the small angle assumption, and so the amplitude and change in length increase with force. And together, these mean that we have axial compression, as we studied before we considered buckling. At the critical force, we suddenly shorten a great deal. But as we exceed the small angles, we start shortening only a little bit as force increases, and we need to ramp force up to continue shortening the beam. And now we consider other types of support reactions. First, we consider a solid support at one end, and the other end being free but under the axial load. This creates only boundary conditions at the solid support that tell you that both the deflection at the solid support and the slope at the solid support are zero. So if we are to draw this, then we can see that we start here flat and we start to curve up. And at some point then we get to this point where F is applied. Now if we continued the shape, we would get back again to no deflection and no slope at twice the length, like a mirror image of this. So what occurred before over a distance of L is now occurring over 2L. That means we can take the equation we derived before and plug in 2L where it used to say L. And this results in the equation that's 1/4, that is 1 over 2 squared, of the Euler buckling force for a hinge in a pin. That is, that a single solid support buckles at a 4 times lower force than one on a hinge in a pin. We next consider the situation of two solid supports supporting a bar. And I say solid-ish here because we're still allowing movement in this direction for that to shorten. So you might imagine a situation where you have a post that is holding up a ceiling, but the ceiling is maybe attached by walls on all sides that really prevent movement in this lateral direction, but it can still bend a little bit, putting force on the post. So this post is just preventing compression of this floor, but its job is not to prevent side-to-side movement. That's already being prevented. So that would create these two solid-ish supports. Now in this case, we have the boundary conditions. V of 0 and V of L are both 0, and the derivative, that is, the slope of the beam at both ends, is also 0. So we see that up here where the position is held at the same level relative to each other. The slope is 0 in both. And in between is the full half sinusoid, which means that the point here, or that L over 2, so if the full thing is a half sinusoid, then the length that we had looked at before, where we said we are not constraining the slope, remember that? Our last boundary condition is a solid support at one end and a pin with a roller at the other. So this might be the same situation we considered before, where there's a ceiling that is solidly held in place but can flex, thus pushing downward on the pole. But this time, the pole is not firmly attached to that ceiling. It's attached, for example, maybe to a floor joist and attached through a single nail in the side that would still allow rotation so that the beam under that could then rotate into the shape that we see here, while the floor stays flat and in place and simply goes down a little bit. So we still allow the movement this way. So in this case, what we see looks about like 1.5 sinusoids. The boundary conditions here are that the deflection is 0 at both ends and the slope is 0 at the left end. Now, while skipping the derivation, we'll just note that what this region here that looks like the half sinusoid we saw before is occurring over around a length of 0.7. So when we plug that into the Euler buckling force formula for the pin and hinge, we now get that the Euler buckling force for the solid support and hinge is twice that of the force for a hinge and pin. That is, this is slightly harder to buckle than one by a hinge and a pin by holding the one support solid. So at this point, we have defined the Euler buckling force for 4 types of columns. The way we know which of these Euler buckling force formulas to use is by asking how the situation you are given affects the boundary conditions. Rarely in real life situations do we have something that's really clearly a solid support or a pin or a hinge, but we can usually logic from the information we know as to whether it's allowing rotation and lateral movement. We just need to remember that one thing that we learned when we first started with the hinge and the pin that said a hinge and a pin is really just drawing the two ends together. Anytime we draw the two ends together, it looks like a hinge and the pin, regardless of where these things are in space. We next ask whether a beam fails due to crushing or buckling. It crushes, that is, fails while it's still straight under axial load, when the ultimate compressive stress is equal to the force divided by area, or the ultimate shear stress is equal to the force divided by twice the area, because the shear stress is half the normal stress in a uniaxial load. So to ask whether this happens before it can buckle is simply to ask whether these occur at lower force stresses than are present at the Euler buckling force. And if either stress then at the buckling force is greater than these ultimate stresses, it will fail while it's still straight and will never have a chance to buckle. That is, it'll fail in here and not in here. So this is worth exploring further, and we will do this specifically for a column with a hinge and pinch supported lengths L apart. And we'll also say it's one that fails due to the ultimate compressive stress instead of the ultimate shear stress under this axial load. And those were the situations that gave us that force and also had us comparing the stress at that force to the ultimate compressive stress. And so combining these things gives us this equation that pi squared times the flexural rigidity divided by the length squared times the area must be less than the ultimate compressive force in order to allow the beam to buckle. That is, it has to buckle at a lower force than it will crush. So we can rewrite this, taking the square root of both sides and, rearrange them and then take the square root of both sides, that the square root of this ratio of e to UCS times pi squared is less than length times the square root of this ratio of I to A. So if we define the radius of gyration as the square root of I over A, this is like a one-dimensional measure of the cross-sectional geometry, thus the term radius, which refers to a one-dimensional property. We can also define L times the inverse of R as the slenderness ratio of a beam. So this property we're asking about here then refers to this expression, whether that's less than the slenderness ratio. So let's revisit that. Now, the maximum strain is the ultimate compressive stress divided by the Young's modulus. We will study material properties more later in this quarter, but for right now, we're just accepting that this maximum strain in most solids is about 0.1% to 1%. And we know that pi squared is around 10. And so this inverse here is about 100 to 1,000 times 10, or about 1,000 to 10,000. So if we put this together, we now put this together. We have this requirement that this expression that relates to material properties must be the slenderness ratio, and that tells us that if a column is slender, it can buckle. We can estimate this by asking if the slenderness ratio is greater than about 300 for more solids, but more precisely, we have to calculate that exact value. And if the slenderness ratio is lower than this, then the column is stout and will fail due to exceeding ultimate stresses during crushing. We have to keep in mind that for columns with other supports, then our Euler buckling force would have been different. And if columns fail to shear, we need to be deriving an expression with respect to the ultimate shear stress instead of the ultimate compressive stress. So these really should be derived every time, but this gives you an approximate idea as to whether buckling or failing due to compressive exceeding ultimate stresses is important. A last consideration when we ask about buckling is a situation that arises with asymmetric cross sections. So ask yourself, why are posts always 4x4 or round and not 2x4s? We use 2x4s all the time for walls, for holding up, for hanging things by. And in fact, we specifically use those 2x4s where the height is in the up position. And that was because I is equal to h cubed w. We want to spend our material making the height stronger if we want that thing to prevent bending under gravitational loads that bend the beam in the y direction. But in a column, there's nothing distinguishing which direction the perturbation occurs. So that is illustrated if we try to buckle a ruler. We see it doesn't matter if we put the long direction on the cross section of the ruler in the y direction. When we buckle it, it doesn't just buckle sideways in the z direction instead of up and down. And so what's clearly happening is it always wants to buckle in the case of the smaller I, that is the one where h is small and w is big, because h is the one that's cubed. You really want to push to minimize that in order to minimize y. So if a pin allows rotation in all directions, then the object can buckle in any direction, and it will buckle in the direction of the smallest I. But if the hinge or pin restricts rotation in one direction but not the other, then we end up with different Euler buckling force equations and different second moments of inertia in the two directions, and we need to determine which way it'll buckle first by calculating both Euler buckling forces using different equations for the Euler buckling force and different second moments of inertia.